Today I'll be explaining one-dimensional motion. So let's start first. We have displacement, velocity, acceleration, and we also have the uniformal constant. We have energy, work, and so on. So let's start first with the displacement. So for the displacement, we have delta x equals to x final minus x initial, and the delta y equals to y final minus y initial, which is the unit, which is meters, which the dimension analysis for it is the capitalized L, which is the length. And then we move on to the velocity. We have like how to find the average velocity equals to vi plus vf over 2, and the unit is meter per second, and the dimensional analysis is the capitalized L over the capitalized T, which is also the dimensional analysis for the velocity or speed. And then we have acceleration. Now for the acceleration, either we have A equals to delta V over delta T, which is like VF minus VI over delta T, and the unit is meter per second square, which the dimensional analysis is L over T squared. That's the dimensional analysis for acceleration. Now, but we have the other situation is when it's uniformal constant. When they mention for you in the question that there's uniformal constant, we're going to use those for kinematic equations. So let's start with the first. So we have delta x equals to half, okay, open brackets, vi plus vf times the delta t, which is the time. Here we have, in this kinetic equation, is like when the acceleration is not there. For the second one, we have vf equals to vi plus the acceleration times the time. Here we have is like when the delta x, which is the displacement, is not included. And then we have for the third one, delta x is included, equals to vi times the delta t, which is the time, plus half a delta t squared. Here the final velocity, or vf, is not included. And for the final one, vf squared equals to vi squared plus 2a, which is the acceleration. The a is the acceleration, and then delta x the displacement. Here we don't have the time. So these are the four kinematic equations that you can use when they tell you in the question uniformal constant. But if there's no, like if it's simply they give you the velocity and they give you the time and tell you to find the acceleration, and they didn't tell you anything about the uniformal constant, you use this equation, which is delta V over delta T. So now let's move on to the energy. So energy, we have non-mechanical and mechanical energy. But we're going to just talk about the mechanical energy over here. Now the mechanical energy, so let's be like mechanical energy, it's split into two. The kinetic energy, and we have the potential energy. Now the kinetic energy does not have branches. It's just half times mass times velocity squared. And for the potential energy, it is branched into elastic potential energy, which is half times k times x squared. This is about how elastic an object is, like for example a rubber or something. And then we have the gravitational potential energy, which is GPE, which is the mass times the gravity, which is 9.8 times the height. So now for the ME, let's say it's going to be like if you want to find the total mechanical energy, and if they gave you the givens and everything, so it's going to be like KE, which is a kinetic energy, plus the potential energy, which is KE plus EPE, which is elastic potential energy, plus GPE, which is gravitational potential energy. Now we have the fifth one is work, which equals to force times distance, and so on. We have more. So now let's go on, let's go to the examples that we have. So now the first question: if a car slows down from 150 kilometers per hour to 120 kilometers per hour, find the average velocity. So here the givens, here we have that we have the VI is 150 kilometer per hour, and VF equals to 120 kilometer per hour, and they want us to find the average velocity. So what we're going to do is going to be like, we go to delta V equals to, we're going to add them, 150, which is VI plus VF. Over here we don't have time given, so we're considering the time as 2, as in the equation here, this formula. This is for the average velocity. So it's going to be like 150 plus 120 divided by 2. So the answer for the average velocity will be 135 meter per second. And that's the answer. And this is the formula that we used. Now the second question, if a car started from rest, so 0, reaching to 130 kilometer per hour, find the displacement if the acceleration was 5 meter per second squared uniformly. So I said when they're in the question, they mentioned uniformly, so we're going to be using the kinematic equations. But first of all, we're going to have to know the givens to know which kinematic equation to use. So we have VI equals to 0 because they said at rest. And we have the acceleration is given, which is 5. Let's change it to kilometer per hour squared, because we have here this kilometer per hour. So kilometer and we need to find the delta x because they asked for the displacement. So what we're going to use is so let's go back to the question. The givens that we have are VI and acceleration. That's it. But we need at least VF. So what we're going to do is we're going to use here two kinematic equations. The first one we're going to use is, no, we don't need to use two. We just use one. So we'll be using this, the last one. Let's say we're going to pick the last one. So we go back. Sorry, we do have the VF. The VF is already given, which is 130 kilometer per hour. So yeah, so it's given, so we're just going to use the last one. So here, because we don't have time, so what are we going to use? We're going to use the last one. So here, because we don't have time, we're going to use the last one. So all the givens are given except time, so we're going to use the last kinematic equation. So VF is already given. So we're just going to go put the equation, VF squared equals to VI squared plus 2a delta x. So we substitute 130 squared equals to VI squared, so it's just nothing, plus 2a, which is 5 delta x, which we need to find. So it will be like 10 delta x equals to 16900. So delta x would be 160 90 meters. Don't forget the unit, which is meters. So that's the answer. Now let's move on to more questions. A car accelerates uniformly at a rate of 4 meters per second squared from rest in 5 seconds. Find the displacement. So here they also said uniformly. Now let's take out the givens. They gave acceleration, which is 4 meters per second squared. From rest, VI equals to 0, time is given, delta t, which is 5. They want us to find the displacements. So what we notice here now, here the VF is not given, which is the final velocity. So we go back to the kinematic equations where VF is not given, so it's the third one over here. So we put the equation delta x equals to VI, and it's better for us if we memorize the kinematic equations so we could better understand. So delta x will equal to 0 times 5. The VI is 0, the time is 5 plus half. The acceleration is 4, which is given, and delta t squared, which is also 5 again. So simply the delta x would be 50 meter. So that's the answer. So now let's go to the last question for this, for the one-dimensional motion, and there could be also other questions. Now we have find the average velocity between 2 to 3 seconds. Number 1 and average velocity number 2. So here we're gonna have, let's start here first. So here we have 2 to 3 seconds. So this is the time, this is the displacement. So 2 to 3 seconds, which is from here to here, so which is 40 and 60. So the displacement, the formula is xf minus xi over the delta t, which is going to be also, let's say, tf minus ti. So 60 minus 40 over 3 minus 2. So the answer would be 20. Now the second average velocity, it's 0 to 1 second, so here's just 20. So xf minus xi, because the displacement, tf minus ti, so 20, we already know that because the displacement here is just 20, it's the same, from 0 to 1, and then 1 minus 0, which is 1, so here it's also 20, and don't forget the unit, meter per second, and this is the answer for the 2 average velocity. And thank you.